A binary that was supposed to write the flag but was deliberately broken. No readable strings, no obvious imports,
and a hidden payload buried inside a custom PE section. This is Binary Instrumentation 3.
We check the import table next, the dump, the list of Windows functions this binary calls. A program that's supposed to write a file should import create file, write file, things like that.
But none of those are here. What we do see is heap allocation functions, some lock primitives, and a message box. The binary can't write a file using functions it doesn't import. So either it's resolving those functions at runtime PEM, which is a classic malware technique called dynamic resolution, or it's loading a second hidden binary that does the actual work. This is called PE manual mapping, or reflective loading. And this is exactly what's happening. We dump the section headers and there it is found, a section called .atom.
Everything else in this binary is tiny. The .text section, 18 kata, the .r data, 446 kilobytes, nearly half a megabyte, sitting inside a binary that does almost nothing on its own. That section is the payload. We peek at its raw bytes pro. The first few bytes are 5 dir. That's the magic signature of lzma compression. Specifically, the outer binary is a loader. It decompresses whatever's inside .atom and executes it in memory. We try running the binary under Wine on Linux. It crashes immediately, meta. A page fault when it tries. Here's what's happening. The loader calls virtual alloc to reserve memory at a specific address. The code doesn't check for NUL album. It just starts copying bytes to address 0, which crashes. This is bug #1. The outer binary is broken on Linux because Wine doesn't give it the exact memory address it wants. But we've confirmed the architecture habu. This is a reflective PE loader, and the inner binary is lzma. We write a simple Python script to pull out the .atom section and decompress it with the lzma module. The result? A valid Windows PE binary, a completely separate executable that was we call it atom.dec. When we run this binary under Wine, and then immediately says I didn't work, and exits. 2 bugs down, 1 to go.
We disassemble main inside atom.dec with objdump. The logic is clear. The program opens a file called
It gets a file handle back OS.
It compares that file handle to the number 10. If the handle equals exactly 10, it writes the flag, quits.
Here's the problem. Windows assigns file handles as opaque integers. The OS decides what number to give you. It will almost never be exactly 10.
This check is meaningless by design, and it's the messed up thing the challenge description mentioned.
At this point, most people would try to patch the binary, or use Frida to hook the comparison at runtime. Because the flag is already sitting in the binary flow, we just need to read it. The disassembly shows that if the check had passed, the program would iterate over an array called flag parts, initialized before main even runs. We trace those strings back to their addresses in the .r data section, and read them directly from the file using Python. 5 strings, all base 64. We concatenate them and decode. And there it is.
The flag is always in there somewhere. Full write-up with every command and disassembly output is linked in the description. See you in the next one.